Morning, everyone. Today's lecture is about analytical methods in GR. And so I will first introduce a bit why we need them, and then tell you what specifically we are going to cover. So I don't know if you still remember, because by now it has been quite a few years. In 2015, around, well, okay, here we are 1 hour different, but in Utrecht at least, it was around shortly before 11 a.m. on 14th September 2015. This kind of signal was seen in 2 gravitational wave detectors, the LIGO detector, the laser interferometer and gravitational wave observatories. They have 2 locations in the US. And they looked for gravitational waves already for several decades, but they had just finished a major upgrade, turned on with improved sensitivity, and both detectors at nearly the same time saw this feature in the data. And because this was seen in 2 detectors thousands of kilometers apart, it indicated it was a real gravitational wave signal. And there were many tests done to kind of be sure it was real as much as could be determined. And it turned out it was actually the signal of 2 black holes of 30-ish solar masses orbiting each other at incredibly high velocities. So these were really many solar masses heavy objects, but moving at about 50,000 kilometers per second and getting faster and faster. And eventually merged together into a single black hole of about 62 solar masses. Here, you might notice if you add up 30 plus 35, it's clearly not 62. Where did this missing mass go? Well, it was converted to energy in gravitational waves. So that's a huge amount of energy. But on Earth, we saw just a small signal that was only visible in these really sensitive detectors. If you think back on what you were doing at this time, you probably didn't notice anything at all. Okay, and now what we are mainly interested in for these lectures is how did we actually know that this kind of signal corresponded to 30 solar mass black holes at so and so many billion light years from us and so on? Well, how it is interpreted really relies on theoretical models. So we take a model, and we will discuss a bit how these are computed. Now seen in orange, and that model assumes it was a binary black hole system with a total mass of 200 solar masses at a distance of 800 megaparsec. And clearly it does not match the data at all. So then we try a different mass. So we shrink the total mass. We see now the oscillations got faster, and here towards the end at least, they match the signal quite well, but the amplitude is. But the amplitude we can adjust by changing the distance. So now we have a waveform that matches the data reasonably well, at least in these later parts. Of course, in the real data, there's still some noise, which is not in the theoretical model. But based on this kind of fit or matching, we could conclude that whatever parameters this best fit model had, that was the true source. So our interpretation really relies on having good theoretical models, because if the model is not accurate or missing some effects, then our interpretation will be biased. And for the data analysis, it's of course much more complicated. One doesn't sit and compare visually. It's a full Bayesian analysis based on some specific criterion of how well the model matches the data. And this is done with millions of waveforms for each event. So millions of models are being tried with over different regions in the parameter space. And then in the end, it's not just a point estimate, but one gets a probability distribution for what were the most likely source parameters. And it's actually one needs, so here we just restrict it to total mass and distance, but in reality, one needs more than 15 parameters to completely characterize the signal. And furthermore, these models are not only used to interpret the data, because actually most signals that the detectors observe are not as loud and stand out so nicely as this first event. They're actually much smaller than the noise floor, but they can still be filtered out because this kind of behavior of the signal has very different statistical properties than this kind of more random noise. So actually the way signals are detected, unless they're super loud, is by having a bank of pre-computed waveforms that are filtered against the data, and then similar to when you look for a Fourier transform to filter out certain frequencies of a system, then that helps the detection. So this is kind of two aspects where models play a really crucial role for gravitation. So I hope I've convinced you. Probably you were already convinced since you're also working in theory. But
question.
Yeah.
So are the models for the noise of the detector like constant in time, or every time you observe a gravitational wave, you have to change the model for the noise? Because something can happen
yes.
and here it didn't happen.
Yeah, so the detectors, they kind of, they also do some injections of signals, of some kind of mock signals to kind of see how does the detector respond and what is, because you inject a well, it's not a signal, but it moves. So these detectors are based on laser interferometry, so they have two mirrors, and the mirrors are moved in a certain way, or at least the control system is changed so that it's equivalent. And then you know kind of what signal you injected and then what comes out of the detector. And yeah, these kinds of tests are being done. Or what is also done is one takes chunks of data, but time slides them between the two detectors, kind of so that the correlation is much larger than the travel time of a normal signal. So you would kind of end up only with noise in the two detectors, kind of to try to characterize what's the background. But that's really an active area where there are specific working groups working on characterizing what is the detector noise, what can be considered above the noise or within the noise. More questions? All right. Yeah. So we clearly need very good models, but these are difficult to compute because even if we just restrict to GR physics, we have to solve the Einstein field equations for the dynamical spacetime of the binary. And you see these equations already in GR courses and so on, and you discuss usually some solutions that have a lot of symmetries, like black holes or cosmological solutions. And there you can kind of, it doesn't seem too difficult to solve these equations. But if for gravitational waves, it's all dynamical space-time. So one cannot assume these kinds of simplifying symmetries, and one has to really deal with the full coupled 10 differential equations in 10 variables that are just a big mess. And it's very intransparent to understand kind of mathematical properties, because also some of the degrees of freedom of these 10 variables are not physical, they're just gauge. But a priori, you don't know which ones to pick. And depending on what gauge you pick, you can end up with a problem that is just mathematically not solvable. So it's quite a challenging task, but there are different approaches that have been developed to tackle this problem. And so what we will focus on for these lectures mainly is kind of regions in the parameter space where we can exploit a hierarchy of scales to set up some approximation methods. And one example that we will also start with is two black holes during the early in-spiral when they are far apart. Then the size of the black holes is much smaller compared to the size of the orbit because they're at large separation. And then that in turn is much smaller than the wavelength of the emitted gravitational waves. And the challenge then is still that we cannot make a single approximation that covers the entire space-time and gives us a full dynamical space-time. But instead, we can make different approximations adapted to each of these regions and then connect them together. And the method of how we want to do this is called the method of matched asymptotic expansions, which is what we will start with. But before getting to that, let me just outline the plan for the lectures. So today we will focus on binary end spirals, treating the two black holes as a first approximation as point masses, because when they're at separation, they act kind of like point masses. And it's only when you go to higher orders in the perturbation expansions that you start to see that they actually have a finite size. And tomorrow we will cover then the signatures of the kinds of objects, so taking into account that these are actually black holes or neutron stars or some other objects, and also discuss the ring-down gravitational waves, because all of this comes under the topic of black hole perturbation theory or relativistic perturbation theory. And yeah, just to say, I think we will not have time to cover more than that, because those are already big topics. So there are a lot of topics we will unfortunately have to leave out, but hopefully the lectures give you some starting point to see kind of the basic strategies that we use for analytical approximations. And then you can do further reading on all of these other topics. I'm also happy to provide references if you need any. So we don't want to stare at this too long, because that's what we will not cover. All kinds of interesting topics. So as I said, now we want to start with the question, well, we've kind of established just from physical intuition that if we look at the binary during the early in spiral, the space-time behaves very differently when we look at different scales. And we want to somehow connect all of this information and understand how does information actually, well, for the first part, we will only focus from the orbital scale, get imprinted in the gravitational waves, and how does the fact that we have gravitational waves at infinity in turn impact the orbit of the binary. And as I briefly mentioned, so the method that is needed to do this, or at least one of the methods that can be used, let me say, and it is commonly used for post-Newtonian calculations, is called the method of matched asymptotic expansions. And if you want to have a really pedagogical introduction, this paper here by William Burke, he was actually the first person who introduced this method for gravitational waves, because nowadays, to us, gravitational waves are physical and we don't have any controversies that they exist. But before, in the 1950s, 60s, 70s even, there were a lot of controversies. Are the gravitational waves even real? Or are they just some gauge constructions, and different calculations gave different answers because it was not understood fully all of how to handle all of the mathematics of finding extracting observables from the complicated Einstein field equations. So this was really a seminal paper. And a lot of what I will cover now to explain a bit of the method is taken directly from this paper. So if you need more reading material, you can find it in that paper. So let's start what's the basic idea with matched asymptotic expansions. And we'll do a simple example. It somehow maybe too simple, but it really illustrates the basic idea. So we want to consider a function. Let's call it f, which is 1 plus x plus epsilon over x, where epsilon is some small parameter, much less than 1. Okay, and well, now, suppose, okay, we don't know this full solution, or, you know, it's a solution to a differential equation we are given. So if someone asks us, well, can you make a perturbative approximation to this function? Sort of the first thing we would do is to write down kind of a perturbation series. We would start with f is some f0 of x plus epsilon f1 of x plus order epsilon squared. Right, this is kind of the first thing you would try to approximate this function. And then, okay, in this example, it's really simple. We can just read off what's this f0. Well, it's just 1 plus x. So we read off f0 is 1 plus x. Okay, and it turns out, so let me also show you what this function looks like. So the full function f, if we just plot it on a plot kind of versus x, and then epsilon is the direction going into the board, we see this f0 approximation that we made works really well for large x, but then it starts to break down as x gets small. And why is that? Well, because when we write down this kind of ansatz, we are implicitly assuming that it is an asymptotic expansion at fixed x coordinate. So, and then as x itself gets of order epsilon, then this kind of series does not really capture all the epsilon dependence because x is now itself order epsilon. So it's not a good way to write down a perturbative approximation. And this is also the reason why this is sometimes called the outer approximation. So let me also write here. So that when we make these kinds of Ansätze, we have to be careful kind of what is implicitly assumed in writing this down. So here we are assuming the limit epsilon goes to 0 at fixed x. And as we said, it's sometimes called outer expansion. And now let me also write down the problem for small x. The ordering of the terms changes. Sometimes if you have a differential equation, for example, you can also see this if, for example, the second derivative of a function is multiplied by epsilon or so. So it doesn't have to be just a simple scaling like this, but in this example, it is kind of visible immediately. So ordering of terms changes. Because now epsilon over x becomes order 1 for x equals order epsilon. And this f0 is supposed to capture all of the order 1 dependence plus small corrections that scale as epsilon. And this is not captured by f0. Any questions about this? Is it clear? Okay, so what do we do? Are we doomed now? We tried something and it failed. Of course, there is a way around that mathematicians have developed. And as we already said, x is not a good variable. So yeah, let me also say for this region of small x, when x is order epsilon, x is not a good variable to keep track of the scaling. with epsilon. And so what do? Well, we want a variable that is of order 1 when x is of order epsilon, so that we can again take a limit epsilon goes to 0, a fixed new variable that works well for this region of small x. So we introduce a scaled coordinate. So introduce a scaled coordinate. Which let's call it big X. And this, how should we choose it? Maybe you tell me what we should choose for it.
Epsilon over x.
Yes. But wait, so you said x over epsilon? Yes. Because then when x is order epsilon, for x order epsilon, and it's kind of, yeah, physically what it does is it kind of stretches the region of small x, because then it makes the region that is of order epsilon size only for this original variable x, it kind of stretches it to be now of order 1. So sometimes this is also called a stretched coordinate or a strained coordinate. Yeah, so maybe let me write it down. And you might have seen similar coordinates, for example, the tortoise coordinate in black hole physics also stretches kind of the region near the horizon. But small x. Yeah, and as I said, it's sometimes also called a strained coordinate. Yeah, just in case you read this in some references. Okay, and then we are now ready to make an approximation using this insight. So if we now take the approximation epsilon goes to 0 at fixed big X, we would write down an inner expansion. We call it inner, kind of, because outer we have there. So for the inner expansion, we would write down f is some other function f0 of now big X plus epsilon f1 of big X plus order epsilon squared. Right? In analogy with what we did before. Okay. And we can again read off what is now this f0. Well, if we write the function f in terms of the big X, so we replace small x by epsilon times big X, then we can see that here this becomes plus epsilon times big X plus now 1 over big X. Don't know if you can still read it. Sorry about the squishing. Maybe, yeah. Okay, it's also simple enough that I hope you can also do it yourself. And now we see that the order epsilon to the 0 term are this one and the 1, as we kind of said before. So we had f0 equals 1 plus 1 over x. Okay, and now we kind of have a similar problem as before. If we now plot this big f0, well, it works really well compared to the full function for small x, but then it breaks down for large x. And when does it break down? When big X becomes large of order 1 over epsilon. And let me see. Yeah, so let's just write it down, breaks down for x order 1 over epsilon, which is large. Okay, so now we have one approximation for large x meaning now the original small variable, one approximation for small x, and both are only valid in either large x or small x region. But there is an intermediate regime, at least in this case, where both of them are not too bad. And this you can see plotted here. If we plot both of these solutions, we had the outer solution, which was just 1 plus x, the inner solution, 1 plus 1 over big X. And there's some intermediate region where both are not too bad. And this we call the overlap region, or in the plot I labeled it intermediate region, where both of them are valid. And the idea is then to kind of match them in that region and then construct a full solution. Okay, so in an intermediate region, both are valid. I mean, this will not always be the case. It's something one has to check. But here we find that, I mean, we can already see by plotting it that it is the case. And so now we again have to kind of characterize what is this intermediate region. So it should be large big X and small x. And again, to characterize it, we introduce another variable that is scaled so that it corresponds to this intermediate region. But we don't know yet what this scaling is. So we introduce a function eta, eta of epsilon, which is kind of intermediate between epsilon and 1. And we don't know yet what this is. We just introduce it so that we can characterize kind of an intermediate region. So
in what sense is the statement that in an intermediate region both are valid? Because of the error is of order 1 over epsilon squared, or?
yes, so this we have to determine what the error is and to what order they match. So this basically, yeah, they have to, in this region, the two should kind of coincide up to some small corrections, where small corrections can scale with epsilon and eta. But we don't know yet what these are.
Yeah, it's gonna tell us what sense this both are valid, because I mean,
Yes. But okay, it turns out in this example it's a bit too simple. We won't be able to, yeah, because we kept only these F0s to really determine the rate. So the statement is also this eta is not just one value. It has to work for a range of values. So it could be like epsilon to some interval between epsilon to the 1/3, epsilon to the 2/3, or something. You can choose anything that is in between just epsilon and 1, but you cannot choose it a priori because this will be determined by the matching. But we will see this in a moment. But it is it is really important that there's some domain, not just one point where they match. There has to be some extended domain where this eta can take on different, different functions of epsilon. Okay, and then, well, any more questions? Also, I think it will become a bit clear once we actually match the solutions. So then, we say this intermediate region, we call it X is order eta. So it's small because eta is less than 1, but it's not yet as small as epsilon because there the solution we know is completely invalid. And correspondingly, big X is order eta over epsilon. So it is large because epsilon is much smaller than eta. So this is now how we kind of parameterize this intermediate region. And we introduce again an adapted scaled coordinate. So this scaled coordinate should again be order 1 in this intermediate region. So what should I choose for the scaled coordinate? Should it be scaled? Perfect. So let's call it x eta because now we have too many x's. So x divided by eta. And it is order 1 when x is order eta. And you can also work out that this is also satisfied. So order 1 for x equals order eta. So now we have kind of adopted a scaled coordinate for the intermediate region. So now the matching, what we call the matching, is now going to be carried out for epsilon goes to 0 at fixed x eta, because again, we need a coordinate that is order 1. So formally, what we should do is, which we will do in this example in a second. So we take limit epsilon goes to 0 of the outer approximation, eta minus f inner approximation, expressed as a function of x eta, and this should be 0, and usually, as we said, only to some order. So we will not achieve in general that this is exactly 0. It will be order epsilon to some power, eta to some other power.
Can you always systematically make that match to the order you want of precision?
Well, if an overlap domain exists, then if you include higher order terms, you should be able to match. That's by definition that the overlap domain exists. But you have to be really careful because if, higher order terms depend on x in some strange way, then you introduce kind of more dependencies on eta, which is supposed to be small. So orders can get shuffled. So there could be maybe a third order that would contribute at the same order as F1 in the matching, because now we are choosing different coordinates and so on. Yeah, so this is the statement. Yeah, maybe if you want in the tutorial, we can do a kind of more complicated problem where you can practice with this if you want. Let's see what we will do in the tutorial. Okay, so finally, now let's implement this. This is kind of a formal condition. Now let's just see how it works in our example. Okay, and so as I said, we're being a bit sloppy here because we only worked out F0. And in principle, we should also have higher order terms to make sure they don't spoil the matching. But here, turns out it actually works. So let's now express our other solution in terms of x eta. Well, we had, so we substitute x is eta x eta. And then the outer solution was just, we had only the zeroth order term, which was 1 plus small x, so 1 plus eta x eta. And the inner solution, we had big X is eta over epsilon x eta. So F0 inner is equal to 1 plus epsilon over eta x eta, 1 over x eta. Okay, and now we are supposed to match them. We are supposed to take the limit epsilon goes to 0 at fixed x eta. So this, if epsilon goes to 0, eta also goes to 0, except not as fast. So this is of order 1 plus order eta. And then here, again, we now take the limit epsilon goes to 0 faster than eta goes to 0. So this term is also small. So it's also 1 plus order epsilon over eta. And we see that if we now take the difference between the two, the ones subtract. So it's 0 plus order eta and epsilon over eta. If we input it into this formula. So that means if we want to achieve a matching, we have to require that these terms and these terms are both small compared to order 1. And okay, here what we see again is just that epsilon has to be smaller than eta and eta has to be smaller than 1, which is already what we assumed. So to really narrow down what is the overlap domain, we would have to go to higher orders. In this example, okay, you will see in a second that the higher order terms don't contribute. But in normal, more complicated problems, then you will find, again, you will get something also for the higher order terms, but there will be different scalings here of epsilon over eta and eta. And then you can determine they only match if eta is between epsilon to the 1/3 to 2/3 or so, something like this. Okay, so now the final step is, maybe let me also write down. So you have it in your notes, terms match to order 8. And as we argued, this can be achieved for eta, between epsilon and 1, and for a range of it. Maybe also write this down so you have the record range of eta. And this is the case in our example. So the final step now, okay, we have the inner and outer approximation. We've shown that they overlap in some domain. The final step is to construct a so-called composite expansion, which combines the two and gives a unified description that is valid everywhere. Composite expansion. And the prescription for constructing these composite expansions is, well, we know, so let's write down the composite. We know we have a solution that works at large X, which is the outer solution. We have a solution that works at small x, which is the inner solution. so F inner. So this will automatically work both for large and small x. However, we showed from the matching here that there is a common content of both of them, which was this term 1 that we saw in the matching. So if we just add these two solutions, it would double count this kind of common content that they have. So we have to subtract it, because otherwise it's double counted and then it doesn't give us the right answer. So minus the common terms. And yeah, these are identified from matching. Is the idea kind of clear? Okay, so finally, let's apply this. And so we had now since we now have kind of taken care of all the scalings with epsilon, let's just express this composite solution where we have to choose one of the coordinates. Let's use the original small x. So we take the outer solution, which was just 1 plus x, and the inner solution, which was 1 plus 1 over big X, which is epsilon over x. And then the common term that we saw in the matching was 1. So adding this up gives 1 plus x plus epsilon over x, which is exactly the original function, which is also why I mentioned that all the higher order terms vanish. And kind of the remarkable thing that has happened now is that using only approximations, we only used always the F0, which was the order 1 piece. So using only calculations at order 1, up to, of course, the rescaling of the coordinates. But we saw that in the composite solution, we did capture all the terms of order epsilon, or at least the relevant ones. So it yields a non-trivial dependence. Non-dependence in the solution. Okay, so this is in a nutshell the basic method. Any questions about this?
So what kind of functions are we gonna want to match asymptotically?
We are going to want to match asymptotically solutions to the differential equations in certain approximations. So in post-Newtonian theory, it is matching a post-Newtonian description with a post-Minkowski description at large distances. Then tomorrow we want to match it to a description of a perturbed black hole.
But then this is very gauge-dependent statements, right?
Yes, so in these cases, the matching has to work up to gauge transformations or coordinate transformations. But in the end, you have to be sure you compute at infinity some observables. So that kind of, and then this information about requiring some observables at infinity, then through the matching translates back to other constraints on the system. Yeah, and this method is actually also used for gravitational self-force calculations, but we will not consider applications, but just it's a very broad tool for these kinds of calculations. Yes.
Maybe this is automatic in the construction, but is it impossible for, say, the inner solution to blow up as you go in the outer region?
Yes. This is what we see here. In fact. Or okay, here maybe it doesn't blow up, but it's yeah, it doesn't work very well. You see here this approximation as zero is this kind of pinkish heat, and the full function is the yellow. And it is definitely possible that it diverges to infinity at some point, and then you have to be sure that your matching domain is not where it blows up.
I'm just worried that if I just add F outer plus F inner,
Yes.
and then I want to evaluate this at any position,
Yes.
one outside the reasonable validity of one of them, I might have a bad behavior.
No, actually, because this also works if you want to, you can match kind of in time to go for a system as that goes through a resonance, for example, where things might diverge, but because you kind of subtract off, yeah, you kind of, it's not easy to see in this example, but you kind of, in this method, you kind of end up subtracting these singularities by this whole construction. Because, yeah, you're kind of subtracting the common terms. For example, if you approach a resonance, then the outer solution would have a kind of divergence near a resonance, let's say, and then the inner solution, as you expand away, might also have that divergence, and then they both have the same divergence for the matching, and this would be subtracted off. Something like this.
Now the idea is that they should start mattering already in the intermediate regions. If they would blow up in the outer region, you would already see them in the intermediate regions and therefore remove them by the match.
Yes, yeah. Because you would maybe have some one solution goes like this, the other one goes like this, and then you would say, okay, the inner intermediate region might be here or something like this, and okay, you wouldn't capture the full divergence, but kind of the onset, and then yes, you would subtract it off.
Somehow the intermediate region has to happen on the divergence. But that is,
No, not well. It could also be, well, if only one function diverges, it could also be, for example, here. It really depends on the problem you're considering.
What kind of functions can we match in this way?
A lot of them. It's well, it is kind of yeah, adapted to these asymptotic expansions, and this I didn't explain so much, but asymptotic expansions are a bit different than convergent series expansions, because for convergent series expansions, you know, you add terms and then you can resum it to some value. For asymptotic expansions, it's not necessarily the case. You might not know what kind of expansion you deal with, but in this asymptotic expansions, they usually don't converge. But for physics, they're still really useful because the first few terms in these asymptotic expansions give a very good approximation to the physics you want to describe. Yes, so I don't remember mathematically what kinds of restrictions there are. Yeah, you could maybe check this paper by William Burke that I referenced here. I think he might discuss a bit more kind of mathematically what are the properties, but it works really for a wide class of systems, and it's actually there's a whole field of mathematics called singular perturbation theory, and this method is one of the methods from singular perturbation theory. So if you need a math book to look, then look for a singular perturbation theory or so.
So since we're doing expansions, is there any theorems or something on like what is the bound of the error of the solution that you constructed?
Well, because the bound on the error will be basically these terms that you neglected in the match. So here, our error would be of order eta epsilon over eta. And yeah, then it depends also, because in physical application, the epsilon will be some physical parameter set by your system. And then you know if you can live with this error or if you need to go to higher orders to reduce it. Or, you know, you might end up finding that there is no longer an overlap domain and you need another expansion to better describe the system also. Okay, more questions? All right, so we spent quite some time on this, but that's okay because, yeah, it's really an important method, and conceptually, this is now what we want to apply to this binary system to connect all of these scales. So I don't know if we want to take a break now before I start something new, or if,
Yeah, we can take a break now. So.
okay.